Color 1, June 24th. Alright. This we are having more and more stuff open. I don't like it. We have to revisit this problem because yesterday, man, that DP was so hard. So hard. But we're going to revisit because there's another method called meet in the middle. So I'm going to read through this and try to figure out how this one is done. So we'll do that. Is that like binary search? I'm not sure, but we're going to do that. But before that, we have, like seriously, we have another one. We have another hard one. Dear Lord. All right, let's take a look at what this one is. You are given an array of distinct positive integers locations. Distinct positive integers locations, where locations I represent the position of city I. You're also given integers start, finish, and fuel, representing the starting city, ending city, and the initial amount of fuel you have. At each step, if you're at city 1, city I, you can pick any city j such that j is not equal to I, and j is within the locations, okay? And move to city j. Moving from I to j represents the amount of fuel you have by this, okay? Please note that this is absolute value. Notice that fuel cannot become negative at any point in time and that you are allowed to visit any city more than once. Return a count of all possible routes from start to finish. Good question. It's a little bit more complicated, but I think it's a good question. We'll have to start today's. I forgot to start. Okay. All right, 2, 3. All right, we have 2, 3, 6, 8, and 4. All right, and then we start. These are locations. Okay, so these are locations. So it's 1, 2, city 2, 3, 4, and 5. Okay, so we start from 1. So we need to go 1, 2, 3. So we're asking how many different routes can we do this? And you can visit as many times as possible, any cities. So we have fuel is 5, and you have to use up the fuel. Okay, you use up the fuel. So we have fuel, start fuel is 5. And you can go from 1 to 3, yes. You can go from 1 to 2, and 2 to 3. This is not necessarily sorted, so it doesn't really matter. So yeah, you can do 1 to 2 to 3. You can do 1 to 4. How can you go 1 to 4? Oh, my bad. 0 index, right? Jeez, man. 0, 1, 2, 3, and 4. So 1, 2, 3. Okay, 1 to 2, 2 to 3. Makes sense. 1 to 4, 4 to 3. 1 to 4, 4 to 2, and 2 to 3. But you can now go 1 to 2 because 2 to 3 is too big. Can you do 1 to 2? Maybe. Because 3 is 8. Okay. All right. So yeah, this is most likely DP. No, not most likely. This is definitely DP. So we have the same problem as yesterday. Need to find the state. Jesus, man. Yeah, DP is just need to find the right state. Okay, what do you think? We have these locations, and we don't need to sort them. We just keep as is. And then we can say we're starting from 1. So what we like to find Okay, so we start from 1. We want to find the total numbers ending at 3. So maybe we can ask, starting from 1, okay? So maybe there could be like we have an index, that's the city. We start from a city. You know what? Maybe that's not what we want. Maybe what we want is you have a start, you have an end, and you have remaining fuel. Okay? So given this, tell me how many different ways, how many different routes is possible. So our solution, our answer shall be dp. We do start. In this case, we have 1, 3, and 5, right? That's what we want to find. And if you look at this, right, the length is 100, which means start, so 100 times 100, that's 10,000, and times fuel times 200, so that's 2 million. I think it's still within the tolerance, so maybe that is the right state to go with. And we can try. And if you want to solve this, basically we have this, right? You have a start and you have an end. How do we find? I mean, the worst you can do. The worst you can do. I don't know. So you have a start, right? We start from here, and we say, yeah, this is what we want, right? 135 is what we want. So now we add 1. Then we can say we can go to any other cities, just not to ourselves. And what else can this? They say all integers in location distinct. That doesn't really help much. So we can go to any of the others, right? So I'm starting at 1. I can choose to go to 2. I can say for city, right, in range n. We're gonna go to all these cities. So I can go to 2, not 2. I can go to 0, right? If I go to 0, then if I go to 0, okay, I can go to 0, and then I need to find 0, 3, whatever, right? So okay, if I go to 0, I need to find dp 0. I go to 0, and I used up 1, so I need to find 0, 3 with 4, because fuel has 4. And I can go to 2, which the next question is from 2 to 3, right? And this one I use up 3, so I have 2 left. And also I can go to 3 directly. Yeah, perfect. I go to 3, and 3 to 3 with 0 left. And the last one I can go to 4, right? If I go to 4, because that's 3, so I have 1, so I have 4 left. Okay, so that's the first level. I find a total of this, total of this, total of this, and I add them together, because that's the routes. And of course, now we go to the second level. This one immediately, because we have 0 remaining, right? And then we check the start. If we have reached, so that's going to return 1, because from 3 to 3 we only have 1 way to go. Does not matter what this is. If these two are the same, then yeah, we're done. So this have 1. Now we go 0, 3, 4. Okay, so we are trying to do 0, 3. Let's delete some of the stuff and see if we can. Yeah, we know what these are. So let's try dp 0, 3, 4. So we are at 0. We're going to try to get to 3, and we have 4 left. So from 0, you can go back to 1. Now here is the thing. Yes, we do go back to 1, because it is possible we can go to back and forth, back and forth, back and forth, back and forth. That's allowed because every city can be visited any number of times. So for here, we have dp, we go back to 1. So the problem is 1, 3. You know what I noticed? I don't really think we need the 3. Because we're not going to go to another location. It's just different starting position. Right? It doesn't really matter. I can put the 3 outside. So I think we don't need this 3. This 3 is not necessary. Okay? And then we just have a global and equal to 3. Then we just compare to 3. So with that, we don't need this. So we say we start from 1 and the fuel. We only have 3 fuels, right? And then next I can say we can go to dp 2 and that'll be 0 left, right? Because it's 4. And I can do dp 3. No, we cannot do dp 3 because I require 6. I don't have 4. So boom, this one doesn't work. But I can go to dp 4. Right, and I have 2 left. And immediately this one will give you 0. Because I have no fuel left and I have not reached the end. So this will be 0. So now with this, I go into this and this. Now 1, 3, right? 1, 3, starting from 1. So basically we can do all of this all over again, right? So this one we can do, 0. That'd be 0, 2. And I can do 2, right? I can do 2, 0. 2, 0 already done, so this one is actually nothing. And then I can go to 3. I cannot go because I'm at 1, need 5, I only have 3. I can go to 4. So I can say 4 with 2 left. And you see we have repeated problem, right? This one, we repeated problem, repeated problem. So I think this might actually work. Yeah, I think this might actually work. The runtime. So the total number of states is gonna be n. We have n, right, on this one, and this is going to be fuel. So n times f, right? N times f, and within each we have to go through. So that's n squared times f. O(n squared f). O(n squared f) is 1 is 10,000, 2 million. Maybe 2 million is working. All right, now let's code it up. Let's hope that this one is good enough. I mean, based on the passing rate, I think this one probably is correct. I mean, it's DP. We all know it's DP, and then we need to find what type of DP it is. And this one has a high passing rate, which means this DP is not really that hard to come up. And this is kind of, I think it's not really that hard to come up. Okay, so what do we need? All right, I need n. N equals to land locations. I need that. And we need a DP. And of course, for that, we need func tools. Let's do ARU cache. And then here we do def DP. I need the start. Let's call it S. And I need the remaining fuel. And this one will give me an integer. All right, then we cache this. Max size equals none. All right, how do we do this? We'll say if, and I'll never have remain become negative. So all we need to do is say if rem is equal to 0, right? And then we say if s is equal to finish, we return 1. That's one step. Else we return 0. Okay. Otherwise, then we can say for I in range n, if I is not equal to the start, then we would do, we say if it's not equal to and we have enough fuel to go there, so will be locations s minus locations I. We need ABS. So if this is smaller or equal to, you know what, maybe maybe if you want to make it easier, now I want to reduce the number of calls. I mean, I can definitely say if rem smaller than 0, just return 0. But I want to reduce the number of calls so we can make it a little bit faster. So I just say if this is smaller than rem to make sure that we will not hit a remaining negative case. And if that's the case, we can say dp will do I and remain minus. We might actually be, let's say, next to remain equal to this. Let's say remain minus this. Okay, and if next to remain is larger equal to 0, then we do next to remain. And we need a current. What's the current? Res. Okay, and we say res equal to res plus this. And let's mod it right here. So we have a mod, it can be 10 to the 9th plus 7. And let's mod it right here. Right, whatever this numbers give you, we'll add it. And then we go through everything. Right? And then once we're done, we are gonna return the result. Okay, then what we want is dp, we from the start with fuel. And then we return this. Let's see if this one is right. Okay, let's pull up some of the test cases. What test cases do we have? We have this, very comprehensive. That's a good test case. Right? All the analysis is built on top of this. And we have these double checking. This one shall be 5. What's the next one? The next one is 0. Good test case. Give us 0. Okay, so this is 0. Let's clean this up. I can do this. Do this. And then this is going to be locations. Start. Finish. Fuel. Count. Oh my god. Location, start, finish, fuel. We're not correct in the second one. We are not correct in the second one. Why? Why are we not correct in the second one? Oh, holy crap. Did you see that? Did you see this one? I mean, it's allowed. We do that. We do that because we return 0 after we do 0. Okay. Okay. So, oof. All right. If this is 0, definitely. If S is equal to finish, I think that's the one I missed. My return is 0. Yeah, that's suspicious. I shall at least return 2. Hold on, but I noticed that there's error in this one, right? There's error because I only return 1 when the remaining is 0. That's the case. That's the case. I only return 1 when remaining is 0, but I shall return 1 when I hit it, right? Which means a res shall equal to int s equal to finish. So when this is equal to finish, I should do 1 already, right? Because that's the current route is good. And then I'll try to do whatever. So let's see if we do this, now we pass. Okay, so just a little bit change here. So we can call this, what do we call this? If the current start is already at the finish, we record the current path, current route, right? We record current route and search for any additional Possibilities. Possibilities. Okay, okie dokie. Okie dokie. Okie dokie. I have probably one more test case that I want to run. So maybe what we can do is, I don't know. Let's do, maybe I'll do 2. You know what? Let's just go for it. Let's just go for it. It looks solid to me. Yep. I mean, it's market is hard, but compared to yesterday, this is like nothing, all right? Yesterday was really hard, but I mean, there's a little secret, a little thing I didn't say yesterday, and I really need to pee. So a little bit of frustration at the end could be because of that. I just really need to pee. But anyway, this one is a medium. I'll mark this one as a medium. Yeah, this is after yesterday's DP. This one is not that hard to identify the state. Okay. So DP S in a rem reports the number of routes that go from S to finish with rem number of fuels. And that's it. And at each S, we simply go through all the locations that reachable, right? Reachable with rem fuels, and add all the routes, all the route counts together. Yeah, that's basically how I would approach it. I'll call it N squared times F, right? Where N is land location and F equal to fuel. Okay, let's just see this. If this, yeah, they use smaller than 0, that's fine. If this answers this, if this answer equal to 1, exactly. And if not, answer equal to solve. Exactly. So that's, yep, no issues. No issues at all. Yeah, yesterday was way too hard, man. Yesterday was way too hard. I shouldn't say way too hard because, you know, there's no such a question as a way too hard. It's just practice. All right, now we're done with today. Let's go to yesterday, the tallest billboard. I remember another problem during my algorithm class. It's cutting rods. Cutting rods is also classic. Minimum cost to cut rods. That one is also hard. If you ask me to solve it right now, I probably cannot. That one's pretty hard. And I think DP, that one is like 3-level DP, right? 3-level DP. And this one is just smart. This one is just smart. This solution, my God. Like how do you come up with this? How do you come up with this setup with DP? Huh? Using difference as the state. I don't know. I guess you just have to do it and then realize. All right, now that's not the goal for today. The goal for today is to go through this, meet in the middle. Okay. So the problem is we have a bunch of rods and we want to pick some, make them together into one giant rods, pick some others, make a giant rods, and we want the 2 rods to have the same length and this giant rod's length to be maximized. Okay, that's a very simple problem. Okay, one possible approach is using a meet in the middle technique. Breaking the problem into halves and solve them separately. It's much faster than this. Dividing rods into halves will bring n to an acceptable level. What do you mean dividing? Half the rods? Split the rods into 2 halves and then generate all combinations of the height of the two. You gotta be kidding me. Of the 2 stands for each half. The steps building the hash set state that stores all distinct combinations from the left half. So we have wait, hold a second. What are you doing here? So brute force. I know how to do brute force. I do not know how to do brute force. Yes. The number of rods given as input, because each rod can be either added to the first, the second, or not be used at all. So there are 3 03 to the n, which is very bad when n becomes large. So we'll brute force it, but we'll brute force it to each half. So on the half, I find all possible combinations, okay? And for each state, I have basically 2 values, a left and right. So we have a left and right on the left and the left and right on the right, and then we can try to see if we can fit them together. Okay, let's think. Let's think. So we kind of know the idea. So we just brute force. I actually have no idea how to brute force this on each side. We'll solve this problem later. So let's say on the left hand side I have a bunch of left and right. On the right hand side I have a bunch of left and right. How do we match them together? How do we match them together? So on the left side I have the left and right, right? And on the right hand side I can, pick and choose the difference, right? The difference. If I have left and right, left height and right height on the left hand side, and they have a certain difference, and the only way to match this with something on the right is if the height, the right have the same difference as the left, then we can match them, right? So the hash map on the left can be created by taking the key as the difference. I think that is where the DP problem, the state for the DP comes into being. Because now on the left hand side, on the 2 halves, right, each half you use a diff to be the key, and the value is going to be the taller, the size of the tall. Because with diff and a tall, you actually you can record this state. So on the left hand side I have all the diffs with talls, okay, the tallest of the tall, and on the right hand side I have all the diff with talls. And then I just go through the diff. Exactly, we go through the diff and add them together and then find out which one is the tallest. Okay, this is called meet in the middle. Anyway, so I will try. So we won't have to find the brute force, right? We'll have the brute force. How do we brute force this? 3 to the n, right? So each one I can choose to put in the first, put in the second, or not put. I think this can be done by a recursion, right? Yeah, it's recursion. I'm the current, and I can decide to put in the left, and I can decide to put in the right, and all I need is the height, right? And I can just go all the way down towards the last one and report. what is the left and right. Okay, let's try this. So this is inspired by the official solution. Okay, official solution of meet in the middle. We brute force half of rods to find all possible sizes, right? Sizes of the two combined rods. This will take O3 to the n, because each individual rod can either be placed to the left pole, right pole, or not used. We can use a recursion, right? Recursion to do a backtracking algo to find all possible left and right pole heights. To record all these pole heights, we employ diff between the two poles as the key, and the value is the highest pole with such diff. The reason of using diff is that for the two halves to combine and produce two poles with the same height, the poles on the two halves must share the same diff. That's it. All right, so I can do DFS. What's called DFS? We can say gen pole heights. Okay. Then I have, what do I have? I have an index. And let's do current rods. How about that? Index is this, current rods is list int. Don't return anything because I'm going to record on the outside. Or left dict equals this, right r dict, okay, equals this. Okay, and we can say 0 0, right, because these are the starting point. But do we even need a starting point? I guess we do not, unless we do default dict. Maybe we can do default dict. What do you think? I think we can do default dict. Let's do default dict. Default dict lambda 1, lambda 0, which is int. Okay, default dict int. All right, so now we're talking. So for each index, I can go two ways. Oh, and also need a left, right. Right, that's the pole heights. Then we say if index is larger or equal to line current rods. Oh, I need a dict as well. The dictionary int. Okay, probably need dict as well. All right, so I can save that. Then d abs left minus right, okay, equals maximum d abs left minus right, maximum left and right. Else, so the current one, I can choose it to put in the left, right? Which means gen poll heights, I choose it, index plus 1, current rod, these doesn't change. The left, I put in the left, so current rods, index, right, D, right? So we can say put index. In fact, I don't even need this. I just need the what do you need? I need the index, the limit, index lim. Okay, so I just need to say if index is larger than index lim, then we do this. Otherwise, I can say put rod's index to the left pole. I don't need to do this, it's just index lim, and there's no current rods, it's just rods. Okay, so I'll gen that, and then I'll gen another one to the right pole. So exact same thing, but this go to the right, and do not use rod's index. Right, so same thing, but do not use, so we don't do anything. So we do that. Okay, we do that. So we do all this. Let me place these down here. Okay. All right. Then we basically say, we call gen poll heights 0. Okay. There's going to be len rods divided by 2. Okay, divided by 2. And left is 0, right is 0, L dict. And then we'll do the exact same thing. It's going to be len rods divided by 2 plus 1. And this is going to be len rods minus 1, right? And this is going to be right. Okay, so we generate the 2. Now we can say for diff, right? For diff taller in L dict dot items. We have a res equal to 0, res equal to maximum res, taller plus r dict diff. And now I return res. Let's see if this one works. This is somewhere to 3. Ain't right. Something's not right. Holy crap. Okay, so we do not have this. Okay, do we always have double it? Do we just double it? The taller. Oh yeah, you don't plus the tall, you plus the short. Yeah, you plus the short, so taller plus this and minus diff. You plus the short. Almost. Number 3, 0, 1, 2. We are right on everything else. This answer is 0, but I got 1. Why? So 2 divided by 2 is 1, so 0 and 1. And on the other side is nothing, okay? On the other side is nothing. So on this side and other side is nothing. Huh. Other side is nothing. How do we handle this? Other side is nothing. But on this side I have difference. Actually, we can take a look. We can say print L dict and print R dict. R dict, difference 3 is 3. Difference is 1 is 2. Difference is 2 is 2. Difference is 0. You should also have difference 1. Oh yeah, 1 is 2. So we got all this. And then you say for this, if it does not exist, right? If it does not exist, which means I should do for this if it's not 0, right? So if r dict diff, if it's 0 with this difference is 0, which means it doesn't exist, then we do this, then we'll pass. Otherwise we will just add a 0 to it and then you will get whatever it is here. Makes sense, right? Makes sense. Yeah, I'll go through the diff 3 and that'll be the taller minus, that'll be 0, and I'll go through 1, diff is 1, taller is 2, and this is 0 minus 1, right? 0 minus 1, that doesn't work. Okay, so with this, let's see if it's correct. Everything passes, we can go for it. O2, right? 2 times 3 to the power of n divided by 2 plus whatever this is, plus m, diff, right? There's all different type of diffs. Let's see, is it too slow for this? No, it's actually not. So I can try this and it gives me a wrong answer. It gives me a wrong answer, man. It gives me a wrong answer, and I know exactly why. I know exactly why. This shall be left dict diff. No, left diff to 0. You look great. This shall be left diff to 0. Trust me, if we do this, I think this one will be correct. Yep, because I need to include on the left hand side, it's not 0 to start with. Let me check everything else. I have the test cases here. So we will get this 100 and 100 with 0. No, not 0. Dude, it's 100. Yep. All right, try it again. Slower. Slower for sure, but it works. And in fact, this one, okay, that's a new technique. I've never seen it before. Called this, what's it called? Meet in the middle. Something to think about. Meet in the middle, right? And makes sense. Oh, they do this. New state. Nah, I like my way. I like my way. I think that's cleaner, right? That's cleaner. And yeah, we'd do it the same way. Anyway, so the meet in the middle, I think the ideal is you can do. Oh yes, I haven't. Oh, I haven't. I'll do it. Yes. All right, so the idea is if we brute force the entire thing, it's too costly, right? 3 to the n. If you brute force the entire thing, it becomes too costly. So we brute force half of it. All right, half of it is good enough because when you brute force half of it, you can create these dictionaries to hold the state. Basically, the best you can do on the left and right, given a difference of the two poles. And then you can do this, simple one to combine them together. This is the origin, right? This is the original solution. And when you get here, then you start thinking, okay, what if I don't go through this generation? And because this takes a long time. If I don't go this, and I'm already using diff as the key and the taller one as the value, then you start thinking, can I use dp, right? To say the dp key is a diff and the value is taller. And then you start to think about this solution, right? Okay, I'm gonna go back to this one. This one, basically you iterate through every single rod. And then for each rod, you have all the difference you created in the past, right? All the difference. And then they also record the highest poles you can get. And then given a new thing, all right, given a new thing, you can create new rods. So you can put on the left hand side, you can put on the right hand side, and you create new diff. And then you can do this very fast. Good. Meet in the middle. So yeah, I don't know. Brute force. Cutting half to do brute force, because 2 times it is much faster than doing the whole thing. Wow, this is a great problem. This is a great problem. A lot of new things to learn here. I hope I can remember all those. Okay, so I guess that's it, but we're still stuck here. I mean, I have a solution for this. I thought about something, but I don't think I have the ghana to do it today. So I'll let it pass. Okay, we can probably do this tomorrow. Tomorrow might be an easy problem, so we can handle this. I mean, the basic idea is still a heap, a max heap to keep the x smallest value. And then we don't use the size of the heap. We keep an external value to keep track of the heap. And then we have another one, a set, to see which values from the heap needs to be popped. And we kind of just juggle all these 3 things together. So that's what I'm going to try tomorrow. Okay, that'll be it. I'll see you guys tomorrow. Adios.